Gamma is a finite group inside the isomorphic group acting freely. So this is space of constant curvature, and you're supposed to show it's symmetric only if gamma is plus minus identity. So we're talking about isometry. So here's a general kind of question. You have a manifold, and you have the universal cover, pi, right? And then you have some isometry downstairs. So what he said is, well, I can lift that because I can look at this composition. That's an isometry. So it must lift to something under this covering, like general covering space theory. And F tilde is a global isometry. Right? These are all local isometries. That's global isometry. This is defined globally. And it's local isometry because everything is local isometry.
But it's not injective.
You have to think about that. It is. Right. So there's some kind of natural relationship, but of course it's not one-to-one yet. So the interesting question would be, this might be useful here. I don't know if you need it or not, but certainly this is a useful question to think about. So relate isometric of M, isometric group of M tilde, and the deck group, which is gamma here, right? So, but here I have a deck group also in this general context, right? So that's something useful to know.
Goes around that equivariant.
Something like that, right? Think about it, right? That's kind of useful. It probably helps to solve that problem, I would guess. Okay. Other questions? Then question? Okay. So we talked about curvature of a symmetric pair. So let me remind you, I say G, K is sigma. Or sometimes I just say G, K if it's clear from context. Is a symmetric pair. If sigma is an automorphism, involution, and K is in between G sigma 0 and G sigma, and K is compact, and K and G have no idea in common. So remember, this means G mod K almost effective, which is a natural assumption. Okay, then we had the Cartan decomposition in this context. G is equal to K plus P into the plus 1 eigenspaces of D sigma on the Lie algebra. So this is always our general setup. We will always talk about symmetric pairs like this. And then we had the theorem that if, two results, right? If X lies in P and Y is a vector field on M, on G mod K, then the coherent derivative is either write down of the killing field corresponding to X in direction of Y at the point P naught. That's probably also a general convention that would be good to do here. Let's say P naught is the base point. Of course, M is G mod K, also identified like this, right? And then in that context, G and P naught would be K. So you can go back and forth between these kind of notations. So at the point P naught, this here exists in the manifold. At the point P naught, this was then the Lie bracket between X star and Y at the point P naught. Was there a sign? I forget. No sign. And then the curvature, there I have to take all three vectors in P, and then R, X, Y, Z, I just write it like this, is X, Y, Z. Again, this only holds at P naught. Is there a minus sign there? Yes, there was a minus sign there. Remember, there's an issue of whether I take the Lie brackets on the manifold or on the space, right? There was this issue that this is equal to minus X star Y star. So here I always want to interpret this as Lie brackets are taken in the Lie algebra. So If I want to put the stars there, put a star here, and this would be a star there. So this would be precisely written down what it means, but one often leaves a star away. Right? So I know the curvature at the point P0, and therefore I know the curvature everywhere. Same with the co-derivative. So this was all. This was proof of this was using some fact about geodesics, which I thought I could do later, but I actually needed it in the proof, which I want to do now. So again, G, K sigma symmetric pair. If X lies in P, then XTX times P naught, so the gamma of T, is a geodesic with gamma at 0 P naught and gamma prime at 0 equal to X, which I remember I can interpret as an element of the tangent space of G mod K at K, which identify with P in the usual fashion, right? So, particularly, this describes all geodesics, right? Any vector in P, that means any tangent vector there. This is what the geodesics look like. And also, I want to add to that the left translations where XPX is the transvection, which we call T sub T, right? Associated to the geodesic gamma. I'll recall that in a minute. So particularly then, of course, this was a general statement, say, then gamma of T is also the transvections applied to the point P naught. But this was true for any transvection, so just as a reminder. So here, kind of all makes sense, right? This should be the transvection. Okay. So that's the statement I want to prove. Okay, first I'm going to do this. So part one, maybe. I will prove this for the following symmetric pair. So I can also take, let me call that G prime, the isomorphic group, the identical component of the isomorphic group. This is not clear whether it's G or not. In fact, in general, it's not. There are examples like flat equivalence space where G was much smaller than the full isomorphic group. And then I have the isotropy, K prime, which is stabilized at the point P naught. And then from our general theory of symmetric spaces, something embedded in here. Yeah. We know that I get another symmetric pair. So then G prime, K prime is a symmetric pair with symmetry as follows. So sigma of G was SGS inverse, same thing as SGS, where S was the symmetry at the point P naught, which is an element of G, of the isomorphic group. So remember, we started with a Riemannian manifold. That's a symmetric space. By definition, it has a symmetry. That's what I mean by these symmetries right here. Then I looked at the full isomorphic group, and then I defined automorphism from the symmetry by conjugation. Right? And then it had, again, this property that for this automorphism, K prime lies in between. So it's a symmetric pair in that sense, and that was a symmetry. This automorphism sigma that's associated to that in this sense here. Okay. And of course, then I get also a Cartan decomposition into the +1 eigenspaces of d sigma. Maybe we should give it a different name because sigma is the one for the pair I started out with, so let's call it sigma prime. d sigma prime. So it now goes from G prime to G prime. It has a Cartesian associate. So in principle, I have two symmetric pairs associated to a symmetric space.
The given involution doesn't have to be the conjugation by the symmetry.
In there it does.
In there, that's it.
But here, no. Here it's given to me. So I still want to discuss a little bit later what's the relation with sigma prime sigma. A priori, I don't know what it is yet. Okay. Sigma prime is defined on a bigger group, and sigma only on the group G. Of course, G sits inside, so G sits inside I0 of M, which is G prime, and K sits inside G prime P naught, which is K prime. Because K was a set of all things in G at fixed point, which means, and that's K prime. Right?
Because the pair is assumed connected.
Yes, so in a symmetric pair here, G is assumed to be connected, absolutely. Would be a mess otherwise. Then I would have to say, well, G and K have the same components, and the quotient must be connected. It's unpleasant, right? So, but this setup is much more natural when G is connected. So that's why here, for this symmetric pair, I take the identical component of the symmetry group, as opposed to the full one. Okay, so now I'm going to prove that if X lies in P prime, then the geodesic gamma of T is XTX times P naught. So that's what I want to prove. For this, let's see, how do I want to start with to do this? Yes. So let's start with the geodesic. So gamma is a geodesic. Gamma at 0 is P naught. Gamma prime at 0 is in the tangent space at the P naught. So I guess let's call it X. And I'll let T be the transvection. What was a transvection? It was a symmetry at time t over 2 composed with a symmetry at time gamma 0. Associated to this geodesic gamma. And then we knew that it's a one-parameter group. So that means the flow of TT is a Killing vector field. And I want to claim that Killing vector field is X. So if I can see that, then I claim I'm done. Because what's the flow? What's the flow of T sub T if X is a Killing vector associated to it? It's just left translation by X dx. Right, if X is my Killing vector field, then this one-parameter group generates a Killing vector field, and that's what I called TT. That's the one-parameter group that generates X, so TT would be left translation by X dx. And of course, another property of a transvection was that gamma T is then T sub T times P naught. Okay, these were all properties. So this and this were the main properties of transvections associated geodesic defined in this fashion. And I want to show that this is true, and then this follows from this. Okay. Yeah. So to see this, what I'm going to do, I'm going to show that let's see. I'm going to show that, that sigma of tt is t minus t. So sigma takes a transvection into the opposite direction, sigma prime. This would imply then that d sigma prime applied to x is minus x. Right? If I differentiate tt, I get my Killing vector field x. So differentiate the equation. This is x, this is minus x. So this implies that x lies in p prime. Right? Because the minus 1 eigenspace of sigma prime, this was in my Cartan decomposition p prime. And let's see, then I'd be done, is that right? Yes, then I'd be done, so if I show this. So let's just crank it out. This is now not hard. Applying the definition of the symmetry. So what's sigma prime? Sigma is conjugation with S. S, TTS. What's TT? That was defined by symmetries, right? Symmetry at gamma of t over 2. Symmetry at gamma of 0, and then composed with symmetry again. But what was S? S was a symmetry at P naught, and P naught is gamma at 0. So that means these cancel, right? This is an evolution. So this is symmetry S, which is a symmetry at gamma naught, composed with S at gamma t over 2. But these are involutions. That's the inverse. So this is the inverse of t minus t, right? The inverse of this here. Since it's an involution, it's just S gamma 0, S gamma t over 2. And since it's a one-parameter group, that's t minus t. Okay, so it's very easy. Sigma prime has this property that it takes the transvection to minus it, and therefore x lies in the minus 1 eigenspace. And that proves this claim right here. So for the symmetric pair, it's given by the full isommetry group. This is true. So now I want to relate the two, right? So these two symmetric pairs, and I want to make the following claim. Like this relationship is going to come in very handy again later on.
You showed that the direction of the geodesic lies in P prime.
Correct. That doesn't imply the proposition yet. That only applies that claim over there.
You know that the transvection is the left translation?
Because what's the flow of x? So in general, right? X, I have an element in G, which is x. Then if I look at the corresponding vector field of the manifold, what is its flow? I claim it's Lxtx. Because how are x star defined, right? X star at any point was take ddt of x tx times p. This was the definition, right? So that means that these things right here, which are left translations, are the flow of x star. Okay. And x was a Killing field associated to this here. So this is the flow of x. On the other hand, for this general fact, this is the flow of x also. So therefore, they're the same. Okay. I think in the notes I give a proof of this, but now I realize it's not necessary. It just follows from general principles. So I think I apply to a point and prove there's equality, but this is not really necessary. Okay, so now let's see what relationship I claim exists. So I have G prime equals K prime plus P prime. K prime is contained in K by definition. G prime is contained in sorry, K is contained in K prime, G is contained in G prime, K prime, G prime with a Fourier harmony group. What's the question? Something still confuses you, right?
It's not clear to me why the transactions are the flow of X.
I define X that way. So I'm not starting with an X here. Right? I'm starting with a geodesic. Look at its transaction. It's a one-parameter group by isometries. It defines some killing vector field. I call that X. And then I'm going to prove this property for that particular X. And what I proved was that X lies in P prime. And this is a flow of X, which is the transactions. So I'm doing it indirectly. Okay. So the claim here, of course, notice that see the tangent space at P naught of the manifold of G mod K is both isomorphic to P and isomorphic to P prime. Using each homogeneous space, I have written the manifold in two different ways, right? As G prime mod K prime and as G mod K. So this is our general identification. But it doesn't mean a priori that they have to be the same, because well, it's no a priori, because it's a possibly different identification. Here I take something in G and identify here something in G prime, identify this here. But I want to claim that they are the same after all. In fact, I'm going to claim P is contained in P prime, and hence P is equal to P prime, since the dimension of P is a dimension of M. So I only have to show an inclusion. P is contained in P prime would imply everything. So how do I do that? And here I'm going to have to use that these are symmetric pairs. This is false in general. If I look at homogeneous spaces, I can think of, say, here's a homogeneous space. G is a subgroup of G prime. This selects transitivity. I can write as homogeneous in the second way. If I now let P and P prime be my reductive complements, there's no reason why one should be contained in the other. So I'm going to have to use a symmetry. So let's take an X in P. What does that mean? That means that D sigma X is minus X. I want to show that the same thing is true for sigma prime, which would then imply X is in P prime. So that's what I want to show. For this, I'm going to show that sigma prime restricted to G is sigma. So there actually is a very simple relation between G prime and G, between sigma prime and sigma. Sigma prime is in the big group. This is a subgroup. I can restrict it, particularly it's invariant, which a priori is not obvious that it takes G to G, and the restriction is sigma. That's my claim. Once I can show this, I'm all done. Right? So if P is P prime, of course, then this statement right here is exactly what I want. Right? Then X and P is in P prime, and that's what I want. Okay. So should I take the transfections or the other ones?
But that is clear because they are isometries.
What does that imply?
They are both isometries fixing the point P.
Yes.
And they have the same differential. Well,
On here, but therefore on here and here also. But is this the same thing or not? Like being the same, that's kind of equivalent, right? To say this is true is equivalent to saying that that this is true. Right, so a priori not clear. So here I want to show that LSGS is left translation by sigma of G. Let's see, is that what I need? Yes. So let's see. So for this I have to, why is this sufficient? So let's go back to our symmetric pair a little bit. So I have G, K, I have sigma. Right? That defines G mod K, it's a symmetric space. And then what's the symmetry at P naught of that symmetric space? And the claim was it was GK goes to sigma GK. So in other words, the symmetry at this point P naught is left translation by sigma G. Comment?
I wanted to know what are we trying to prove now?
We're trying to prove.
The restriction part.
Why is.
Prime restriction.
Yeah, we're trying to prove this. Why is this? Why does that mean that? Let's see. Sigma prime was conjugation with S. Okay, so let's maybe. So sigma prime of G is SGS. And of course, sigma of G is sigma of G. Right? I want to show that. What do I want to show? So what does this mean here? This means, so maybe i.e. if G lies in G, then sigma of G should be sigma prime of G. And what's sigma prime of G? That's SGS. So that's what I want to show. I want to show that this preserves G and is equal to sigma on G. So take a G in there. What's sigma prime of G? On the other hand, is SGS. And I want to show it's sigma of G. So I want to show this equation. These are assumptives on the manifold. So I'm going to view them as left translations. That's how they act on the manifold. So if I can show that the left translations are the same, then the elements are the same also, because they're the same isometry. Okay, that step was missing. So let's try to show that. So I want to show that left translation by SGS is equal to left translation by sigma G. Let's apply it to K. What's LSGS applied to, what should I call it? R times K as a coset in G mod K. So that's LS, LG, LS applied to RK. What's L? What's LS applied to RK, I claim, is sigma of R times K. Because what's LS? LS is a symmetry at the point P naught. So now I have sigma S. LS is the symmetry at the point P naught. And the symmetry at the point P naught, on the other hand, was given by HK goes to sigma HK. Using now the other description, I have two descriptions of the manifold as G mod H and as G prime mod H prime. On G mod H, what does the symmetry look like? Did I just erase that? Was like this here. This is a symmetry described on G mod K. Symmetry on G prime mod K prime, of course, in the manifold must be the same. There's only one symmetry at the base point. So this is what it looks like on G mod K. And on G prime mod K prime, the symmetry was conjugation. So
not the symmetry, the involution.
that was the involution, but the involution acts on the cosets by applying it to the element G. So I guess we're going back and forth here. There's several different ways of interpreting things, which can be a bit confusing. So for G prime or K prime, I guess I have two ways of looking at it. So I have the symmetry at the point P naught. Then I have the automorphism, which takes G to conjugation by S. And then, of course, G prime, K prime, sigma prime is a symmetric pair. But for a symmetric pair, if I look at this as cosets, this takes place on the level of the isomorphic group. If I look at it as cosets, then it always takes gk to the automorphism applied to G times K. That was a general principle for symmetric pair. Of course, in our case, this is now SG, SK. So where are we? We're trying to show this, right? So I apply it. I apply it to a coset. Of course, I also got S as another identification. S is also left translation by S. But S was the isometry, which is my involution at the point. So can you got it as an isometry? But if I identify M with the homogeneous space G mod K prime or G mod K, then how does something like this X? It takes H. What am I doing? RK. I'm doing RK. RK to SRK. So left translation by S applied to RK. So that's another fun identification. S is the same thing as LS on the manifold. Very confusing. So let's go back here. Maybe we can probably erase this now. Make it clear. This is equal to, I'm starting to get confused myself. I claim it's L SG applied to sigma of R times K. So S was my symmetry. LS is my symmetry. My symmetry is either induced by sigma or by sigma prime, because they're both symmetric pairs. So here I can write a sigma. So then this is equal to left translation by S applied to G sigma R K. Just putting this in here. This is my symmetry, but that's the same thing as sigma. So it's sigma of G, sigma squares identity, times RK. So in this sense, well, and this is left translation by sigma of G applied to RK. So indeed, this LSGS acting on the manifold RK is the same thing as L sigma G applied to RK, and this implies they're the same. And this then implies that SGS is sigma of G. And now I'm done. Okay, a little tricky. But this fact is useful fact to remember. If I have a symmetric pair, the symmetry might be larger, but whatever the symmetry of the big one is, it just restricts to the, whatever the involution of the big one is, just restricts to the involution of the little one. Okay. Probably has to sit down and piece digest all these identifications a little bit. Too many identifications. Rather confusing. Okay. So that's the geodesics in the manifold. So I can actually compute them very easily, right? It's typically impossible to compute the geodesics. Even for homogeneous space, it's usually impossible to compute the geodesics. It's just too complicated. Famous example is, if I'd say take left invariant matrix on SO3. Simplest Lewis you can think of. Take a left invariant on SO3. So it's a Riemannian homogeneous space. Right? SO3 acts transitive by definition. A homogeneity may or may not be larger, but typically it's the same. Describe the geodesic of this metric. So what are the geodesics? In fact, this has a physical interpretation. It's a spinning top, motion of the spinning top. Right, the thing that you rotate. There's a couple of geodesics you can recognize. Those are the ones that you see when the top spins and becomes periodic. That's a closed geodesic in this metric, left invariant metric on SO3. And if it crashes, that's one of the other geodesics which are enclosed. But if I want to write down explicitly what the geodesics here look like, that's quite difficult. You may, in this case, you may be able to do it in terms of elliptic integrals or something like this. I don't remember, but even the simplest case is very difficult to compute the geodesic. Typically, it's impossible. If I take a larger dimension of Ribu with some left invariant metric, you can't really compute the geodesics. So this makes symmetric space really special and nice. I can compute the geodesic very easily. And I compute the curvature very easily, and the cone derivative. So everything's easily computable. That makes symmetric spaces so nice. Okay. Now I want to prove the following properties. Okay. And now define what's called the type. So that's a very important concept. So I start with a symmetric pair. I have the Cartan decomposition. And I have B the killing form of of the D group G, so on, of G. It's defined in the Lie algebra. And then I say G mod G comma K has compact type if the killing form on P is negative, has non-compact type if the killing form on P is positive, and Euclidean type if the killing form of P is 0. So I have something of compact type, non-compact type, and Euclidean type. So I divide my symmetric space into these categories. Now, in this generality, a symmetric space doesn't have to have either type. It could be some kind of mixture. But if it's irreducible, then it has one of those types. So let me now write down a couple of properties of these types. So this is really important. This distinction is crucial in understanding symmetric spaces. So, same setup. Part A. If G mod K is irreducible as a symmetric space, remember that meant that at K acts irreducibly on P. Right here, Cartan decomposition. P was an identical tangent space. I have an isotope representation on the tangent space given by the stabilizer. When I identify this, we think it became the adjoint representation. Right? So here, in this context, at K to P, and became another way of using the isotope representation. And if that's irreducible, I call the symmetric space irreducible. Right? So just a reminder. So then the conclusion is, then G comma K is either compact type or non-compact type or Euclidean type. So in the irreducible case, it really is a division into three different types. Right? In each type, I want to understand a little bit better. As a consequence of what we did earlier, if the symmetric space is simply connected, then M is M0 cross M1 cross M2, where M0 is Euclidean type, and M1 is compact type, and M2 is non-compact type. Right? From our general theory, we knew that every simple connected symmetric space can be written as part of irreducible ones, and irreducible one is of one of these types. So here, collect the Euclidean types and collect all the factors which are compact types, and collect all the factors which are non-compact type. So now I have a product. So therefore, it's sufficient to understand the types. Understand the types, you understand the symmetric spaces, up to coverings. But in fact, so we usually just try to understand simply connected symmetric spaces. If you want to ask the general question of what quotients are also symmetric, one can answer that, but it's a little bit nasty. I think Wolf in his book does that. I'm not going to do that, so understanding simply connected ones is sufficient. Several other properties. Let me maybe prove this first. So certainly A implies B from our general theory decomposition. So let's prove A. But that's also a clear claim. Right, so on P, we have an inner product which is invariant under at K, because at K expositometries. That's my representation. And B on the whole Lie algebra G is also invariant under at K, because these are inner automorphisms even on the Lie algebra G. Automorphisms preserve the killing form, so inner ones preserve the killing form. So that implies now, by what we call Schur's lemma, that one is a multiple of the other. So B restricted to at least P is equal to lambda times the metric on P, where lambda is some constant. So, of course, the metric is positive definite, right? So whether B is positive, negative, or 0 just depends on the sign of the lambda. If lambda is positive, B is positive. If lambda is negative, B is negative. Lambda is 0, B is 0. Okay, so B has to have one of these properties just because P is a multiple of the metric. So that implies A. So I have lambda negative, lambda positive, lambda equal to 0 as the types, as the three types. Okay, so that's one motivation, that you really have this very different behavior as far as killing form is concerned, but also as far as the manifold is concerned, they're very different. So if G comma K has compact type, then G is compact, and then also G mod K, of course, is compact. So compact type is where the manifold is compact, and G is a compact group of isometries. Okay. If it's a non-compact type, it's the same thing. So G non-compact type implies G and M non-compact. That's what the name comes from, right? So it comes from, is a manifold compact or not? That's compact type and non-compact type. And then the third one, if G mod K is of Euclidean type, then the curvature is identical to 0 of the manifold, so it's flat. So, which means that M tilde is isometric to Rn. So if G mod K is of Euclidean type, it's a manifold which is flat, so its universal cover is flat and simply connected, and then by classification that must be isometric to Rn. So Euclidean type just means a quotient of Rn. Okay. So these are the uninteresting types, if you want to, the ones which are flat. So therefore, this compact type, non-compact type, those are the interesting ones, and those you want to study. Okay, so how do you do that? There was characterization of when a group was compact. So notice that all I have to show that G is compact, and here that G is non-compact. But if G is compact, the manifold is compact. If G is non-compact, K is always compact. That means the quotient is non-compact. So it's the compactness of G that I want to look at. Well, we can decide that in terms of the killing form, I claim. So I'm going to show that compact type implies a killing form negative definite on G, on R of G, which then by our previous theory, we did earlier in the semester, implies G compact. Right? A Lie group where the killing form is negative definite is a compact Lie group. And another property we had is that if G is compact It may not be true that the killing form is negative definite, but at least it's smaller or equal to 0. Like if G has a torus in it, for example, the killing form is 0. So this means that hence if B on P is positive, so maybe I should say this first. The following statement finishes everything. So let me write down the claim, and then we can just finish it right here. G, K symmetric pair implies a killing form of the Lie algebra G restricted to K is negative definite. So that's always true. Nothing, no assumption of type or anything. It's always negative definite. So this would then imply, if I know this, then B so that's then, okay. Sigma is an automorphism. So D sigma is an automorphism of the Lie algebra. Respects the killing form B. Every automorphism is an ensemble of the killing form. I claim this implies that K and P are orthogonal. Right, there's a +1 eigenspace, that's a -1 eigenspace. Automorphism respects it, multiplies everything by -1, must be 0. Okay. Just plug the isometry in there, the automorphism. So if B on P is negative, this implies B on all of G is negative. Because K and P are 0, on K is always negative, so it's also negative on P, it's 0 on all of G, and this implies G compact. Of what I said over there. Right. Lie group with negative killing form must be a compact Lie group. Then if B on P is positive definite, this implies G is non-compact, since otherwise B on is smaller or equal to 0. Right, so it's positive here, negative here, and they're orthogonal. Can't be compact. So the claim indeed implies these two statements. Notice this statement here is clear from what we did earlier, because what did we say about the curvature is given by Lie brackets. For x, y, and z and p. So Euclidean type let me come back to that. I need one more statement there, but it's here I can add to that if and only if P, P is equal to 0. But let me get back to that. It's a separate issue. Let's just finish compactness and non-compactness of the group and of the manifold. So I need to show this here. P on K is always negative. Cannot make sense because K is a compact Lie group. So at least the killing form of K is negative. Well, of course, it could be torus, so smaller or equal to 0. So even that's not quite clear. The killing form of K is smaller or equal to 0, that's true, but that's not what we're claiming. And in fact, K doesn't have to be semi-simple. It can have some Euclidean factor on it. So G on killing form on K of K can be 0. What is true? This is smaller or equal to 0. But it can have a kernel. But here we look at the killing of G restricted to K. So, pardon?
Isn't K an ideal?
K?
Yes.
No, it's a subalgebra. But K and G are not supposed to have any ideals in common. Right, that's
K is the Lie algebra of the subgroup of the K.
yes.
It is a normal subgroup.
Why is it normal? Why should it be normal? No, G, it's a manifold. Yeah, yeah. This would mean G mod K would be removed. If K is normal in G mod K is a group. Our manifolds are symmetric spaces. They're not groups in general. Right. So in fact, in this language G mod K symmetric pair, the assumption was also that G mod K is almost effective, which was if and only if G and K have no ideals in common. So as far from normal as you want to, K is never allowed to be normal in G, then it's not effective. Even worse than that, they're not allowed to have an ideal in common.
P and K.
No, K and G.
G is the big one.
G is a big one, K is a stabilizer, P is a complement, the tangent space. And effectiveness has to do whether G and K have an ideal in common. G and P, so what were the relationships in general? So you have this kind of Cartan decomposition. We had K, K and K, that's just a subalgebra. We had K, P containing P, that's reductive decomposition. And for symmetric space, we had P, P containing K. Right, these are the relationships. So when could it be an ideal? Like if K an ideal, all these would have to be 0. All the weights would have to be 0. For P to be an ideal, all these Liebweights have to be 0. P has to be Abelian to be an ideal. Like that would be equivalent, right? P is an ideal if and only if all the little brackets in P vanish. So that's certainly, that's going to be the flat case. Those are the ones that we aren't interested in. And K an ideal means all these Lie brackets vanish here. And that's the infinitesimal isotropic representation if you want to. So that would contradict this effectiveness. So neither K nor P are ideals. Never. So that's important. So yes, certainly if it was an ideal, then this would just be the killing form of K. But it's not, so this is a little bit different. So here, choose an inner product on all of G such that at X, for X in K, X by isometries. And I can do this since K is compact by assumption. Right, I have the group K. I do have an inner product on P invariant under X, but I want to find out the whole Lie algebra because killing form will take the trace on the whole Lie algebra. So let's define another inner product by just taking my compact group K, which acts via the adjoint on G, average it to make it K invariant. It's not G invariant because G doesn't have to be compact, but at least it's K invariant. That means that at X, where X lies in K, must be skew symmetric, not by isometries. At would be by isometries. Okay. Yeah, it's killing, right? It's skew symmetric. Right, that would be killing. So at X is skew symmetric. So what happens if I take an X in K now, and I take B of X, X? This was minus trace at X squared. By definition, right? But now Adex is Q on the whole Lie algebra. Right. And I take a square of such a skew endomorphism. Well, what's the normal form of a skew endomorphism? It's one of these matrices 0A minus A0. It has block form, right? And 0B minus B0 and so on. Every skew symmetric matrix I can bring to that form. When I square it, so if I take such a matrix and I square it, I get minus a squared, 0, 0, and so on. So that says that the trace of the square, so it's a diagonal matrix like this, would be the sum of all these AIs. So it's small equal to 0, certainly. It's minus the sum of squares. And it's equal to 0 if and only if Rx is at 0. Because then all these have to be 0 for this to be 0. Right? What does that mean? So that means that X lies in the center of the whole algebra G and in K, since we start with something in K. Right? Well, so if the center of G and K have something in common, that's an ideal. Right? So, but center of G intersected K is an ideal in G and K. The center is an ideal, and it lies in K, so that's also an ideal in K, but also an ideal in G, in the big one, but effectiveness implies it's 0. So that implies X is equal to 0. So Bx, X was small equal to 0. Equal to 0 if and only if it's 0. So that means B is negative. B of X, X is negative for all X and K. That was my claim, right? That Bx is the killing form of G is negative on K. For any symmetric pair, it's a useful fact for a symmetric pair. Now, combined with the definition, the property of compact Lie groups, that implies these two important facts. So division into compact manifolds and non-compact manifolds. And we're going to see next week that there's a beautiful duality between the two. I can go from compact type to non-compact type in a very natural way, and the other way around. There's a one-to-one correspondence between the two. And this one-to-one correspondence is similar to the duality between the sphere and the parabolic space, curvature 1, curvature minus 1. And to go from a sphere to parabolic space, I multiply by I. That's the idea. Like, so if I take a sine function, multiply by I, I get the sinh function. Sine for positive curvature, sinh for negative curvature. Kind of makes sense. And that's what I'm going to do in general here for these metric spaces. I'm going to multiply by I. So kind of just advertisement. When G is K plus P, a symmetric space, I define a new one, G tilde, as K plus I times P inside the classification of G, where I'm allowed to multiply by I. And then I claim that this is this G tilde, comma K, is again a symmetric pair. And if this one is compact, and this one is non-compact, and conversely. So it generalizes kind of the analog between curvature 1 minus 1 to the whole class of symmetric spaces. And whatever curvature I have in the compact case, in this duality, I have the negative of that curvature to the non-compact case. So curvature is also very naturally the same. So that's a beautiful concept, this duality. I'll do that on next week. Okay. Euclidean type, let me finish that off. So this was B on P is equal to 0. What does that mean? Well, I also know that B of K comma P is equal to 0 by our general principle. That means that P is in the kernel of the killing form. Right, so B with, if one variable is P, then any inner product with something in either P or in K is 0. So it lies in the kernel of the killing form. But kernel B is an ideal in G so what does that imply? Remember what I just said? We said that, well, P comma P is contained in K, and K comma P is contained in P. So for P to be an ideal, this is only possible if the D brackets between P and P are 0. Right, so that's what this implies. That's only possible if all the brackets in P vanish for P to be an ideal. Well, and then we know that this implies that the curvature between x, y, and z is equal to 0. At the point P naught, and therefore everywhere, so the manifold is flat. Okay. So there's two ways to characterize a Euclidean type. Either all Lie brackets in P vanish, or the manifold is flat. It turns out I can go backwards here, which I don't want to do now. It's really equivalent, which isn't quite obvious, right? Here I'm saying the triple Lie brackets vanish. Here I say the single Lie brackets vanish. But I claim it's actually the same thing. I don't want to do that now. Let's see, any other properties of types? No, that's it. Maybe one more property I can finish with, the curvature. G comma K compact type implies the section. So I like to call it sec, because it's a little bit more suggestive than K as a section curvature. The letter K, in fact, where does the letter K come from? Like that Docao and everyone else uses. Why K? Why not C? Curvature starts with a C. Right? In English, in Portuguese, in almost every language starts with a C, except for in German. That starts with a K. It's Komong. And there's a basic book by Groma Klingberg-Meyer, which, when I was an undergraduate student, was a Bible in geometry. And he knows by K, and then later when it was accepted by everyone. Now they all call it K, but I don't like it. How do you know K is curvature? For Ricci, you have a knife notation, not Rich. And that's clear, right? Scalar curvature, either S or scalar. So one often nowadays uses this notation for scalar curvature. It's obvious what it is. That's scalar. That's obviously richer. Well, that's obviously section curvature. It's a better notation. So I'm going to use that. G comma K non-compact type implies section curvature small equal to 0. And we just saw that the Euclidean type implies 0 too. Implies section curvature dead 0. So this type distinction also is reflected right away in the curvature. Greater equal to 0 is compact type, small equal to 0 is non-compact type, 0 is Euclidean type. So depending on what substrate you're interested in as far as curvature is concerned, there's a lot of work on manifest non-positive curvature. You've probably seen things like Priceman in a course in geometry, right? So for these, a large class of examples are all symmetry space of non-compact type. They're the most basic examples of manifold with non-positive curvature. Okay. And similar for greater equal to 0, symmetry space of compact type. It's a large class of examples. So to see this, I just use a formula for the curvature and add to that the following remark. So what's the sectional curvature of a two-plane xy? So let's say they have unit length and are orthogonal, so an orthonormal basis on my two-plane. And this is just R of x, y, y, x in my sign notation for curvature, which is opposite to Decamo. Right? Well, what would you say the curvature is? It's given by Lie brackets. Right, this here is a triple Lie bracket, xy comma y, inner product with x. So this is symmetric on P, right? So x and y lie in P. But on P, the metric is a multiple of the Killing form. And ADX is Q-symmetric in the Killing form. So that means if I think of this as a multiple of the Killing form, I might as well use this Q-symmetry right away. So this is equal to, what do I want to switch? Let's switch this one and this one. And then I have to play with the minus sign. So x, y, x, y. Well, let's put the lambda in there, right? So metric is 1 over lambda times that. Because now the sign of lambda matters, of course, right? So lambda positive was non-compact type, lambda negative was compact type. Here's a sign problem. I want to claim compact type greater equal to 0.
Why should we put the lambda? Because we interpret it as B, as lambda B. We will use that add epsilon, add y is q. So as to apply it in M. And if we return to the notation of inner product.
Well, the inner product, this here only exists on P, right? It's only defined on P, but this is defined on all of G. Where does this lie here? So where does this element lie? X and Y are in P, right? So it lies in P, comma P, which is in K. So these vectors lie in K. So strictly speaking, it doesn't make sense to talk about the metric. I have to take the Killing form for this to make sense. So here, right, this inner product is 1 over lambda times the Killing form, then use Q-symmetry, and I get this. Of course, then notice that, what can I say about this inner product here? B of something in K, comma K. Remember that B restricted to K was negative. So this expression here is small equal to 0. It might be the Liebeck vanishes, right? Small equal to 0. So now the sign lambda tells me, right, if lambda is, if I have compact type, that was lambda negative, then this one is positive. And then if lambda is negative, since this is positive, this is negative, the other way around. And of course, if Lie brackets vanish, so if P comma P is 0, then the curvature is 0 without looking at skew symmetry. So that's the proof. But even more than that, I have a formula if you want to. So I could say the section curvature between x and y is plus or minus kind of norm squared x and y if I want to. Plus or minus depends on whether lambda is positive or negative. Right, so up to scaling, say, right? I could make lambda equal to plus or minus 1 up to scaling. It's kind of the same metric, right? And then this would be the plus or minus this norm squared in the Killing form. Plus or minus the Killing form, depending on which metric it is. No, actually the Killing form, because this lies in K. Okay. So in particular, 2-plane has 0 curvature. if and only if the Lie brackets vanish. So I can see flat planes very easily just by Lie brackets. Right?
So they will give an integral foliation.
Pardon?
If I have a flat plane, can I see my left translations as a family of planes?
Yes.
How it integrated because of that?
Yes, but one has to prove that. So I claim, in fact, the more general statement, say if I have a subspace L inside P, which is a tangent space, with the property that Lie brackets and L vanish, which this would be true if this is zero, I will two-plane like this. This implies that X of L is totally geodesic in the symmetry space. So if I look at the image of the exponential map, that integrates totally geodesic and flat. So that integrates to something that's flat. That's kind of what you're saying. It doesn't give me a foliation. It gives me something going through the foot point, which is flat. Right? If I left translate, of course, I also get other flats if you want to, but there's no reason why it should be foliation. It might intersect somewhere. Right? But it gives me lots of flat submanifolds. And for a two-plane, in this case, so lots of flats. So Lie bracket 0 means lots of flat surfaces inside the manifold. Okay. In fact, this motivates the following definition. I should finish with this. Pardon?
Thinking of why it's not foliation. Why would they intersect if they belong to different leaves? Because they are integrals and manifolds in disjoint orbits.
Well, so take a submanifold inside G mod K, right? I claim this can. What does it miss? What does it mean for this to intersect? I claim this will certainly happen in general. What does that mean? Well, even if G lies in K, right? Even that's even worse. That makes it obvious. If G lies in K, it fixes the base point, right? It takes L into another manifold containing the same point, but it's going to rotate somehow, because K acts on tangent space by its isotope representation and rotates the tangent space into something else. That's again not going to be flat. So these this would never give you a foliation. Left translating things will never give you a foliation. But it will give you something that's isometric, particularly in this case, you get lots of flats. From one pair like this, you get lots of flats in your manifold. In fact, this helps you define what's called the rank of a symmetry space, which I should talk about next week. Okay.